Hi everyone, welcome to yet another video in our cardiovascular unit. In this one we're going to start looking at some of the functionality of the heart leading into topics revolving around blood pressure. And then after today we will have one more lecture left looking at how blood pressure is regulated, and that will wrap up everything with our cardiovascular block. So, as always, let's go ahead with our not really attendance questions. First, what is PR or peripheral resistance? Next, which chamber or chambers of the heart eject blood? And third, what prevents backflow of blood in the heart? So go ahead and try to answer those. Hopefully you've done that, so let's see what the correct answers are. First, what is peripheral resistance, PR? We discussed that very early on in this block. I think it was in the very first lecture of cardiovascular when we were looking at blood vessels. PR, peripheral resistance, is the resistance provided by the blood vessels against the blood, or the way that I described it was, how easy is it for blood to move through the vessel? Next, which chamber or chambers of the heart eject blood? This would be the two ventricles. The right ventricle ejects blood going towards the lungs, and the left ventricle ejects blood going towards the tissues of the body. And third, what prevents backflow of blood in the heart? This would be the four valves, the left and right AV valves, and the left and right or pulmonary and aortic semilunar valves. So these are going to be a very important topic today, and those valves, just like we saw with the veins, they open to allow blood to flow in one direction, but they close when blood tries to backflow in the other direction. So make sure to keep that in mind as we start talking about functionality of the heart. And we're going to begin with something called the cardiac cycle. And really, the cardiac cycle is another way of saying one complete heartbeat. And this is going to cover all of the events that happen inside the heart during one heartbeat. And it's divided into a few different periods. So the first one, the very beginning of the heartbeat, is called the period of ventricular filling. So during this time, it's exactly what it sounds like. During this period, the ventricles will be filling with blood. So what happens during the period of ventricular filling? Well, blood is coming back to the heart from the lungs or from the body, and the atria are filling with blood, so the pressure inside the atria is rising. Now, here I'm going to take kind of a detour for a moment and introduce something that we're going to be hearing a whole lot about, and that is pressure. We're constantly going to be talking about pressure rising and pressure dropping, because pressure really is what is going to dictate the movement of blood. It's all going to come down to pressure. So as we are bringing blood back to the heart, that blood is entering the left atrium and the right atrium, and as the atria fill with blood, pressure inside those atria is going upward. It's climbing. And the moment that the pressure in the atria is greater than the pressure in the ventricles, that is going to cause the AV valves to open. And once those AV valves are open, blood starts to move from the atria, where pressure is higher, towards the ventricles, where pressure is lower. Remember, everything wants to move from an area of high pressure to an area of low pressure, just like everything wants to move from an area of high concentration towards an area of low concentration. Same thing. When those AV valves open, blood moves from the atria towards the ventricles, from an area where pressure is high towards an area where pressure is low. At this time, this is when the SA node fires. So over here, this is called the Weger's diagram, and it's really showing a whole lot. But up at the top, the very top line, this is the EKG. So right here is where we are. Right immediately before the P wave, the SA node fires. So we get the P wave, the atria depolarize. Now this flat spot right after the P wave, what happens there? That's when we get atrial systole. The atria contract. Now the atria we saw in lab, not a very strong contraction. They just barely squeeze just to push the last little bit of blood into the ventricles. Now, the atria, they do not completely empty because blood is constantly coming back to them. But they do squeeze a little bit more blood into the ventricles. So now the ventricles are at their fullest point. The volume of blood in the ventricles right now, when they are at their most relaxed and most full, is called the end diastolic volume, the EDV, end diastolic volume, which means the volume of blood in the ventricles at the end of diastole. Remember ventricular diastole? The ventricles are completely relaxed and they are full of blood. The volume of blood is the end diastolic volume. In the average healthy adult white male, that is about 130 milliliters of blood in each ventricle. So, all of that is happening at the period of ventricular filling. Now, if we look down on our Weger's diagram, what it's actually showing us is during the light blue area here, the same thing is happening here. So this is pressure. This is volume. Down here it's showing us what the valves are doing, if they're open or closed. And down here it's showing us what is the blood doing and what is the heart doing. So this just kind of puts everything together. Now we're on to the second phase. This is the period of ventricular systole. So this is when the ventricles are going to squeeze, they're going to contract. So during ventricular systole, that electrical impulse is going to spread. We're going to get our QRS complex. Now, during this time, that QRS complex, what we're seeing is, think back to our autorhythmicity pathway. That impulse, that action potential is spreading down the bundle branches up through the Purkinje fibers and across the walls of the ventricles. So we get ventricular depolarization. Now, right behind that, remember the atria are repolarizing and going into diastole. But we are looking at the ventricles right now. So the ventricles are depolarizing. And as we talked about previously, anytime the ventricles depolarize, what's going to immediately follow that? Ventricular systole. So the ventricles, now think about this in slow motion. Even though it happens very quickly, think about it in slow motion. The ventricles start to squeeze. And as they start to squeeze, the pressure inside them is rising. They are squeezing on the blood inside the ventricles, the pressure there is rising. So as pressure rises in the ventricles, the moment that the pressure in the ventricles is higher than the pressure in the atria, what's going to happen? The blood is going to go backwards. It's going to go from the ventricles towards the atria where pressure is lower. But we have those AV valves, and as blood tries to push back the other way, it forces those AV valves closed, so blood does not go into the atria from the ventricles. And remember, we have those chordae tendineae holding on to those AV valves so that they do not close and then reflect back up into the atria. They do not go beyond closed. Meanwhile, remember, we're thinking in slow motion. The ventricles are still squeezing, and the pressure is continuing to rise inside the ventricles. Now, the moment that the pressure in the right ventricle is greater than the pressure in the pulmonary trunk, the pulmonary semilunar valve opens. The moment that pressure in the left ventricle is greater than the pressure in the aorta, the aortic semilunar valve opens, and blood is ejected from both ventricles. From the right ventricle, blood is ejected into the pulmonary trunk. From the left ventricle, blood is ejected into the aorta. So, pressure in the aorta right now, as we are pushing blood into it, is 120 millimeters of mercury. That number might sound familiar, which we will talk about. But right now we are ejecting blood from the ventricles, and on the left side of the heart, we are ejecting blood into the aorta, filling it with blood, raising the pressure in the aorta up to 120 millimeters of mercury. Now, blood is getting pushed out of the ventricles. So as that blood is ejected from the ventricles, now I will say they are not completely empty. When the ventricles eject blood, they do not eject all of the blood. They eject a portion of it. The volume of blood that is left in the ventricles after ejection is called the end systolic volume, the ESV. The ESV, the end systolic volume, is the volume of blood left in a ventricle at the end of systole. Another way to think about that, the end systolic volume, is the volume of blood left in a ventricle after blood has been ejected. Okay, so we saw the end diastolic volume when the ventricle was completely full was about 130 milliliters. We now squeezed the ventricles. They contracted, and the blood that is left in the ventricles at the end of systole, the end systolic volume, is about 60 milliliters of mercury. So we started at 130. We are left with 60. But what happened to the other amount? There was a lot of blood, but now there's just a little blood. Where did the blood go? It was ejected from the ventricle. And that is called the stroke volume. Stroke volume is how much blood was ejected from the ventricle in a beat. So let's say that kind of in a more proper way. Stroke volume is the volume of blood ejected from a ventricle in one heartbeat. Stroke volume is the volume of blood ejected from a ventricle in one heartbeat. And the way to calculate stroke volume is EDV minus ESV equals SV. End diastolic volume minus end systolic volume equals stroke volume. So we saw 130 milliliters minus 60 milliliters equals 70 milliliters. So stroke volume for the average healthy adult white male is approximately 70 milliliters per beat. So now, the third stage is isovolumetric relaxation. Now that's a mouthful, so let's unpack this and see exactly what it means. Iso, remember, means equal or the same. Volumetric, a measurement of volume. Relaxation. What this means is the ventricles are relaxing, but the volume of blood inside of them is not changing. So let's see what this actually means and what's happening. We have just previously filled the ventricles with blood and then ejected blood from the ventricles. There's a little bit of blood left in each of those two ventricles. Now, the ventricles, if we look at the electrical event, the ventricles are repolarizing, and we go into ventricular diastole. So this is the T wave and shortly after the T wave. Ventricles repolarize, we get the T wave, and then ventricles go into diastole. We get that flat spot there. As the ventricles relax, what's going to happen? The pressure inside of them is going to drop. So pressure in them is now dropping lower and lower, and at the moment that the pressure in the ventricles is lower than the pressure of the pulmonary trunk on the right side or aorta on the left side, blood is going to try to backflow into those ventricles. But just like we saw with the AV valves, the moment blood tries to backflow into the ventricles, that's going to force the semilunar valves closed. So once the semilunar valves close, pressure continues to drop in the ventricles. And what happens? The atria, like we saw in the very beginning, are going to continue filling until pressure in the atria is higher than pressure in the ventricles. Or now that we've seen the whole thing, we could say it another way. Pressure in the ventricles continues to drop until it is less than pressure in the atria. Now the AV valves open and the whole thing happens again. Ventricular filling, ventricular systole, isovolumetric relaxation. All of that is happening during one complete cardiac cycle or one complete heartbeat. So now let's start talking about things that can influence that heart functionality. Let's talk about cardiac output. So now we're starting to learn terms that are going to be related to blood pressure again. Previously, we learned about peripheral resistance. We learned about vasodiameter, vasoconstriction, vasodilation. Now we have seen stroke volume. We've seen end diastolic volume, end systolic volume. Now we're going to start all applying that to factors related to blood pressure. So, cardiac output, usually abbreviated CO. Cardiac output is the volume of blood leaving a ventricle in 1 minute. Don't confuse that with stroke volume. We learned stroke volume just a little bit ago. Stroke volume was the volume of blood leaving a ventricle in 1 beat. Cardiac output is the volume of blood leaving a ventricle in 1 minute. Now, the next term is pretty self-explanatory. Heart rate, abbreviated HR. Now, cardiac output, CO, is found by using the equation stroke volume times heart rate. Let's put that all together. Cardiac output, the volume of blood leaving a ventricle in 1 minute, is equal to stroke volume, the volume of blood leaving a ventricle in 1 beat, times heart rate, the number of beats per minute. So cardiac output, the units are either liters per minute or milliliters per minute. Stroke volume is milliliters per beat. Heart rate is beats per minute. Cardiac output, either liters per minute or milliliters per minute. Stroke volume, milliliters per beat. Heart rate, beats per minute. Now, cardiac output in the average healthy adult white male is approximately 5.25 liters per minute. Now, cardiac output at rest is a steady approximately 5.25 milliliters per minute. Sometimes we need to adjust that. Sometimes we need to regulate that. Maybe we need to lower it if it gets too high. Maybe we need to raise it if it gets too low. We want it to remain around 5.25 liters per minute. So if we know that CO is equal to SV times HR, well, if we need to regulate it, if we need to raise or lower cardiac output, how would we do that? Well, we would do that by either raising or lowering stroke volume or by raising or lowering heart rate. So we can adjust or regulate cardiac output by adjusting or regulating stroke volume or heart rate. Now, let's first look at stroke volume regulation. How does our body regulate stroke volume? How does our body maintain or adjust the volume of blood getting ejected from the heart? Well, first thing is I want to refer you to the last page of your cardiovascular outline. The last page of the cardiovascular outline is going to be a blood pressure chart, and we are going to see these things on that blood pressure chart. Underneath stroke volume, you will see preload, venous return, contractility, and afterload. Those things regulate stroke volume. If you change either or any of those things, it will change stroke volume. So, let's look to see what these things are. Well, preload is kind of synonymous with EDV. They are almost the exact same thing. And what I mean by that is preload is the degree of stretch on the ventricle muscles. So the muscles of the ventricle, the degree of stretch on those muscles is the preload. So what is it that causes stretch? Well, the volume of blood in the ventricle, the EDV. When EDV goes up, we're stretching the walls of the ventricles more, so preload goes up. When EDV goes down, there's not as much blood in the ventricle. We're not stretching the walls as much, so preload goes down. So EDV directly affects preload. They are not exactly the same thing, but we kind of refer to them as the same thing. Now, why is preload or stretch important? How does that impact stroke volume? Well, back in Bio 137, when we were learning about muscle tissue, one of the things we saw near the end of that chapter was if you stretch muscle just a little bit, it will contract harder. That is because of something called the Frank-Starling mechanism. The Frank-Starling mechanism says when muscle is stretched a little bit, it can contract with more force. That's because when we stretch muscle a little bit, what we're actually doing is allowing more cross-bridge interactions to form. And if there are more cross bridges forming, then the heart can contract with more force. And if the heart contracts with more force, what happens? We eject more blood. Another way to say that, if preload goes up because EDV went up, then stroke volume will go up. Up here, if stroke volume goes up, well, cardiac output will go up. Now, there's another term here, venous return, VR. Venous return is the volume of blood that is coming back to the heart. So, more blood coming back to the heart. This is also going to affect preload. If venous return increases, then end diastolic volume is going to increase. And if end diastolic volume increases, preload increases. The stretch increases. And if preload increases, stroke volume increases. If stroke volume increases, cardiac output increases. Same thing if venous return went down. If venous return decreases, then everything would decrease. Think about when you exercise. When you exercise, you're moving your skeletal muscles. That's one of the things that caused venous return to increase. If venous return increases because you're exercising, well, your cardiac output is going to increase. Now let's change gears a little bit and look at something called contractility. Contractility is the contractile force of muscle at a given degree of stretch or at a given length. This can be a little bit tricky to understand, so let's relate it to preload. If I have two muscle fibers and I stretch one of them a little bit and the other I do not, is the one that I stretched or the one that I didn't stretch going to contract harder? Well, preload says the one that I stretch a little bit is going to contract harder. But contractility puts a little bit of a twist on that. Contractility says, what if I have two muscle fibers, but both of them are stretched to the same length? Which one of them will contract harder? Well, they should contract with the same strength if they are stretched the same. But sometimes there are things that cause one of them to contract harder. This is what contractility is. Let's say I have two muscle fibers stretched to the same length, and one of them I give a little bit more calcium to, and one of them I give a little bit less calcium to. Now, even though they're stretched to the same degree, one of them is going to contract harder, the one with more calcium. So we can say the one with more calcium has greater contractility. Anything that affects how hard a muscle contracts at a given degree of stretch is called an inotropic agent. Another way to say that is anything that increases or decreases contractility is called an inotropic agent. There are a few different things that impact contractility. One of them is sympathetic nervous system activity. The SNS impacts contractility. It increases contractility. When SNS is down, it decreases contractility. But since SNS, when it's active, it increases contractility, we say the sympathetic nervous system is a positive inotropic agent. Epinephrine, thyroxine, glucagon, those things are all positive inotropic agents. Also, calcium. Calcium is a positive inotropic agent. Anything that increases contractility is a positive inotropic agent. Anything that decreases is a negative inotropic agent. But really, it all comes down to calcium. And what I mean by that is all of those other things that I said were positive inotropic agents, really what they did was they made the heart muscle cells more permeable to calcium. Sympathetic nervous system activity makes the heart more permeable to calcium. Thyroxine. Remember what thyroxine is? T4, back from the endocrine chapter. Thyroxine makes the heart muscle cells more permeable to calcium. And calcium helps the heart contract harder. Okay, now moving on, afterload. Afterload is the pressure in the aorta just prior to ventricular ejection. Let's think about that. The pressure in the aorta before we start pushing blood into it is the afterload. Why is that important? Well, looking at the left side of the heart, as we go through ventricular systole and the ventricle starts to contract and pressure starts to build, when did we say that the aortic semilunar valve opened? It was when pressure in the left ventricle was greater than pressure in the aorta. So, if pressure in the aorta goes up, well, now that means the left side of the heart has to squeeze harder before blood can be ejected. The higher the afterload, the harder the left side of the heart has to squeeze before those semilunar valve on the left side of the heart opens. If the afterload is higher, then it takes longer before the aortic semilunar valve opens. and there is more pressure in the aorta. So all of that together means we are resisting blood ejecting from the left side of the heart. When afterload goes up, less blood leaves the left side of the heart. Another way to say that is as afterload goes up, stroke volume goes down. And if stroke volume goes down, cardiac output goes down. So those were factors that affected stroke volume. But the other way that we can impact or regulate cardiac output is by regulating heart rate. So let's talk heart rate regulation. The average healthy adult white male has a resting heart rate of 75 beats per minute. Anything that adjusts heart rate up or down is called a chronotropic agent. Remember, inotropic agents regulated contractility. Chronotropic agents regulate heart rate. And we can see the various chronotropic agents also on our blood pressure chart on the last page of this outline. So, the autonomic nervous system regulates heart rate. Remember, the autonomic nervous system was the parasympathetic nervous system or the sympathetic nervous system. SNS, your fight or flight response, uses epinephrine and norepinephrine. Both of those are positive chronotropic agents, meaning they increase heart rate. If we increase heart rate, we increase cardiac output. Parasympathetic nervous system uses the vagus nerve to control heart rate. And when we are talking resting heart rate, remember resting is our key word there. Resting means the parasympathetic nervous system is in control. And that's what sets that 75 beats per minute. So when you are at rest, another term for that is vagal tone. Vagal tone means the regular, basic background signal sent through the vagus nerve keeps the heart beating at 75 times a minute. It's slowing the heart down. So the parasympathetic nervous system, using the vagus nerve to release what was the parasympathetic nervous system neurotransmitter? Acetylcholine, ACH. So parasympathetic nervous system using the vagus nerve releasing ACH onto the heart slows heart rate. PNS is a negative chronotropic agent. It lowers heart rate, which lowers cardiac output. The Bainbridge reflex. We are going to test this in lab, and the Bainbridge reflex is a reflexive activity of the heart that causes your heart to beat faster in response to increased venous return. So let's see what that actually means. When there is a sudden increase in venous return, remember the blood coming back to your heart. When there is a sudden increase in venous return, it's going to stretch the right atrium. Another name for the Bainbridge reflex is the atrial stretch reflex. So, blood coming back to the heart faster than usual all of a sudden stretches the right atrium. That actually triggers your sympathetic nervous system. So the sympathetic nervous system is activated when there is a sudden increase in venous return stretching the right atrium. That causes an increase in heart rate, which increases cardiac output. Why is that important? Well, if you have a sudden rush of blood back to the heart, and if the heart did not start beating faster, the blood would pool at the heart. There would be a pooling of blood at the heart. And that could potentially risk something like blood clotting. Remember, stagnant blood or blood standing still for too long is a risk for blood clotting. The Bainbridge reflex is a sudden increase in heart rate when there is a sudden increase in venous return. Chemical regulation, there are various chemicals that either increase or decrease heart rate. Epinephrine and thyroxine, for example. Thyroxine, again, T4. So both of these, like we just saw, increase the heart's permeability to calcium. Well, in addition to being a positive inotropic agent, calcium is also a positive chronotropic agent. The more calcium enters the heart, the faster the heart can depolarize and result in systole. So, more calcium, increased heart rate. Things that increase calcium increase heart rate, which in turn increases cardiac output. Now, there's something that's not listed on here, but two other things that increase or decrease heart rate: fever. Fever will increase heart rate, and cold temperature will decrease heart rate. Think about if you've ever heard the stories of someone falling into a frozen lake or something. When they pull them out, their heart is either stopped or it is beating very, very slow. But once they're warmed up, it starts beating normally again. That's because cold temperature decreases heart rate. Let's talk about some disorders related to what we've just talked about. Well, tachycardia and bradycardia. Tachycardia is a heart rate over about 100, 120 beats per minute. Bradycardia is a heart rate under 60 beats per minute. Atherosclerosis. This is what happens when there's plaque building up in the arteries. And plaque building up in the arteries, well, it makes it so that the pressure in the aorta and other vessels is elevated. And like we just saw a moment ago, if pressure in the aorta is up, that's increased afterload. It makes the heart work harder. So that's how something like high blood pressure is bad for your heart. It causes your heart to have to work harder to eject blood. Chronic hypertension, same idea. High blood pressure that lasts for a long time keeps that afterload elevated, keeps an ongoing extra exertion on the heart. Pulmonary congestion and peripheral congestion. Okay, so this ties into the circuits of the heart. Remember the pulmonary circuit and the systemic circuit? Here, let's think of left side heart failure or right side heart failure. Well, if the left side of the heart begins to fail, what is it going to do? It is going to not push blood to the body efficiently. And that's going to mean that blood coming back to the left side of the heart backs up. So pressure prior to coming back to the left side of the heart increases. Where is that blood? It's around the lungs. So as pressure in the lungs builds, what we see is fluid leaving those capillaries because the pressure, the hydrostatic pressure in those capillaries increases. Fluid builds up in the lungs. That is called pulmonary congestion or pulmonary edema. Now, if the right side of the heart fails, we're not pushing blood to the lungs as efficiently. So blood coming back to the right side of the heart begins to back up. Blood coming back to the right side of the heart, where's it coming from? It's coming from the body. So blood backs up in the body. Pressure builds up in the body. Fluid starts to leave the capillaries because the hydrostatic pressure there is greater. Where's that fluid going to end up? It's going to end up out in the tissues of the body. So something like in the arms or the legs, really common in the legs, that's peripheral congestion or peripheral edema. So how can we help with this? Well, diuretics. What do diuretics do? They make you pee. So if you're peeing, you're losing volume. You're lowering the volume in your body. So lowering the volume lowers blood volume. If we lower blood volume, there's going to be less pressure. Blood pressure medicines that lower afterload, either by causing vasodilation or by lowering volume or by helping with that plaque buildup, cholesterol. So things that lower afterload can help with that. Digitalis. That comes from this plant up here called foxglove, which is a very common flower garden plant. Very dangerous, but this is what they make digitalis out of. Pretty to look at, dangerous to eat, but digitalis is extracted from foxglove, and digitalis increases contractility, which is good because it means that the heart does not have to work as hard in order to still contract hard. We can allow the heart to contract more efficiently by increasing contractility. So now we've talked about cardiac output, we've talked about heart rate, we've talked about stroke volume. We're going to now build on that and talk about blood pressure and learn some terms to wrap up this lecture before we start talking about blood pressure regulation in our next lecture. So, blood pressure. Normally we see it written in the form of 120/80 millimeters of mercury or something similar to that. Now those two numbers, the top is called the systolic pressure and the bottom is called the diastolic pressure. So let's first look at systolic. Systolic arterial blood pressure. That's the 120. That's the top number. It's the greater number. And systolic blood pressure is the pressure in the aorta during ventricular systole. That's how we get it. Systolic arterial blood pressure is the pressure in the aorta during ventricular systole. And it is determined by the force of contraction of the left ventricle. If the ventricle contracts harder, we push more blood into the aorta. The aorta fills with more blood, pressure rises higher. If the left ventricle does not contract as hard, less blood is pushed into the aorta, so the pressure does not climb as high. So systolic arterial blood pressure is the pressure in the aorta during ventricular systole. Diastolic arterial blood pressure. This is the bottom number. It is the lower pressure. So diastolic blood pressure is the pressure in the aorta during ventricular diastole, when the ventricles are relaxed and they are not pushing blood into the aorta. So this is just pressure in the aorta without any influence from the heart itself. And this is determined by peripheral resistance in the aorta. So when we're not pushing blood into the aorta, there's still blood in the aorta, we're just not pushing it in from the heart. And that the aorta, remember, squeezes against the blood. Any vessel squeezes against the blood that's inside of it. So that pressure that's felt inside the aorta when the heart is relaxed, that is peripheral resistance of the aorta. Now, pulse pressure is the difference in those two. Systolic pressure minus diastolic pressure is called the pulse pressure. Pulse pressure by itself does not really tell us too much, but we will use this number in a calculation in just a moment. So, systolic pressure, the higher number. Diastolic pressure, the lower number. Pulse pressure, the difference in the two. So let's learn about something called mean arterial pressure, or MAP. Mean arterial pressure. This says, well, blood pressure rises and falls. When the heart beats, well, we go up to 120. When the heart relaxes, we go down to 80. And it's constantly going up and down with every beat of the heart. Systole up to 120, diastole down to 80. But MAP is going to take that pressure and get what is essentially an average. Now, mean and average are not the same thing, but they are similar enough that we're going to use them interchangeably. So we will say mean arterial pressure is the average pressure in the vessels. MAP is the force that actually propels blood. And the way that we find MAP, or the mean arterial pressure, is by taking 1/3 of pulse pressure and adding diastolic pressure to it. I said it that way for a reason. You have to take 1/3 of pulse pressure first before adding diastolic pressure to it. Anytime that you calculate this, the most common mistake I see is students say diastolic pressure plus 1/3 pulse pressure, and the way that that works out is diastolic pressure plus pulse pressure over 3, and that does not give you the correct answer. The best way to do it is find pulse pressure, divide it by 3, and whatever answer you get, add diastolic pressure to it. The reason we use this is because the heart spends more time in diastole. Once you've got diastolic pressure plus 1/3 of pulse pressure, that's MAP. Another equation that you can use to find MAP is cardiac output times peripheral resistance. Cardiac output, how much blood leaves the heart per minute. Peripheral resistance, how easy is it for the blood to move through the vessels, gives us the mean arterial pressure. MAP is equal to CO times PR. Now, depending on if you've looked ahead at our blood pressure chart, this may look a little bit familiar but odd. If we look at our blood pressure chart, right across the top it says blood pressure is equal to cardiac output times peripheral resistance. Blood pressure is equal to cardiac output times peripheral resistance. But how can that be? MAP is equal to cardiac output times peripheral resistance. Well, the reason that can be is because MAP is blood pressure. They are the same thing. It's just when we talk about blood pressure, we have two numbers, systolic and diastolic. MAP, we average them and get a single number. but they are the same thing. So here is the blood pressure throughout the vessels of the body. Early on, I said that the further we get from the heart, the lower the blood pressure. This shows us that. Blood pressure drops as we move further away from the aorta or from the heart. But also here we can see systolic pressure and diastolic pressure and mean arterial pressure. Here at the aorta, the difference in systolic pressure and diastolic pressure is pretty significant. But as we move away from the heart, not only does blood pressure drop, the difference in systolic pressure and diastolic pressure becomes less. Once we get to the arterioles, well, past the arterioles, it's just a single pressure. There's not a difference in systolic and diastolic. And as we continue on through the capillaries, through the venules, through the veins, we can see that blood pressure really drops a lot. And as I mentioned, the vena cava, by the time we get there, it is almost zero. It is 2 or 3 sometimes, is not an unusual vena cava pressure. So here is what I just mentioned. Blood pressure is equal to cardiac output times peripheral resistance. We are going to reference our blood pressure chart, and it is extremely important to know this chart. I say know it so that you can see it with your eyes closed. That might be a little bit of an exaggeration, but you do need to very, very strongly know everything that's on that chart. And in our next lecture, which is the final lecture of this chapter, we will be using that chart to draw out how different factors affect blood pressure. We will be using flow charts, so make sure to have quite a bit of spare paper with you for our next lecture. And I will talk to you next time.